entropy as a measure of the efficiency of a binary inquiry. The entropy of a random variable x can be interpreted as the minimum number of binary questions, on average, that need to be asked to determine the identity of a random value of x. Example 1. Let x be the random variable for a fair coin toss. In the last section, we calculated the entropy to be 1 bit. This means we should be able to ask just one binary question per coin toss in order to determine the outcome of a random toss. This is clearly the case since either of the questions, is the outcome heads or is the outcome tails, is sufficient to identify the specific outcome with certainty. Example 2. Let x be the random variable of a die roll for a 6-sided fair die. Since the outcomes are equally likely, we can use equation 5 to obtain an entropy value of 2.585 bits. This means that on average, we should be able to ask approximately 2.6 binary questions per die roll in order to determine the exact values of the die in a sequence of random rolls. Since we cannot ask 2.6 bits regarding the outcome of a single roll of the die, we would need to ask at least 3 binary questions in order to guarantee that we can determine the outcome with certainty. A binary decision tree can be used to model the various paths we might take as we ask our questions. The goal is to ask the most informative questions, ones that resolve the most uncertainty regarding the identity of the specific outcome of the random variable. Decision tree, a flowchart-like structure in which each internal node represents a test on an attribute. For example, whether a coin toss comes up heads or tails. Each branch represents the outcome of the test, and each leaf node represents a class label. The paths from root to leaf represent classification rules. In general, a good strategy is to divide the data in half, or as nearly as possible, and then to ask the following yes-no questions. Is the value of the randomly rolled die among the numbers 1, 2, or 3? Or is the value of the randomly rolled die among the numbers 4, 5, and 6? The answer to either question will narrow the possibilities down to 3 distinct values. Once these 3 values are identified, we divide the pertinent set into a singleton and a doublet, such as the set consisting of 4 and the set consisting of 5 and 6. From here, there are 2 possibilities. 1, we have found the exact outcome of the die roll, or 2, we divide the doublet into 2 singletons, such as 5 and 6 becoming the singleton set 5 and the singleton set 6. Below is an example of a binary decision tree in which we identify the outcome of the roll to be 5. So if we use a binary decision tree as depicted above, what is the average number of questions per die roll that would need to be asked in order to identify the specific value of a random die roll? To answer this, we first need to determine the lengths of paths, branches, and then the number of paths of each length that end at a singleton. The 2 question branches are paths of length 2. The 3 question branches are paths of length 3. The corresponding number of each type are listed below. Hence, the average number of questions per die roll that were asked is 2 times 2 plus 4 times 3 divided by 6, which comes out to be approximately 2.667. We compare this answer to the entropy of x, which is log base 2 of 6, which is equal to 2.585 bits. Observe that the entropy calculation of 2.585 bits is smaller than the 2.667 number of binary questions. Recall that the entropy of a random variable x can be interpreted as the minimum number of binary questions, on average, that need to be asked to determine the identity of a random value of x. Therefore, the entropy for a fair die roll is a lower bound for the average number of binary questions that you would have to ask in order to determine the value of a particular roll of the die. In general, you may not be able to attain the lower bound using a binary inquiry scheme. But an economy of scale kicks in when you consider sequences of random variables of x and are judicious in designing your binary inquiry, as the next example demonstrates. Example 3. If you consider tossing a fair die twice, you can reduce the average number of binary questions per die roll from 2.667, as before, to 2.611. But how? By formulating questions that involve more than the outcomes of a single die roll, you can tease out more information per question. I illustrate this idea on the next page, where I reduce the average number of binary questions per die roll from 2.667 to 2.611, which is only 1 percentage point away from the lower bound set by the entropy of x. To mitigate tedium, I will complete the binary decision tree for 1/4 of the data. Then, by symmetry, the average number of questions per die roll for this fourth of the data will also be the average for the entire binary decision tree. The full set of possible outcomes for a double die roll is as follows, where the first digit in each double-digit number is the value of the outcome of the first die roll, and the second digit is the value of the outcome of the second die roll. Here is our partial binary decision tree of a double die roll. Observe that for the binary decision tree above, we have the following. The number of 3 question branches is 7. The number of 4 question branches is 2. But to arrive at the starting set 11, 12, 13, 14, 15, 16, 21, 22, 23, 2 binary questions would need to be asked. Thus, the true lengths of the question branches are: the number of 5 question branches is 7, the number of 6 question branches is 2. Hence, the average number of binary questions per die roll is 1/2 times the quantity, 7 times 5 plus 2 times 6, that sum divided by 9, which comes out to be approximately 2.611. If we use the same system of binary questions for the other 3/4 of the full decision tree, we will find that the average number of binary questions per die roll needed to be asked to arrive at each of the 36 outcomes of a double die roll is the same as the above. In summary, we reduced our initial estimate of 2.677 binary questions on average per die roll to about 2.611 questions. This brings us considerably closer to the minimum value set by entropy, which is 2.585. Interpretation of decimal answers. We can interpret our answer of 2.611 binary questions per die roll as telling us that if we were to roll a fair die, say 10 times, we would expect about 26 binary questions to be enough to determine the actual outcomes of all 10 rolls. In the next section, we give a final interpretation of the entropy of a random variable as a measure of surprise. In information theory, it is formally called surprisal. Roughly speaking, The more surprise we experience upon observing a particular outcome, the more information that outcome provides. Said differently, when an unlikely outcome occurs, it is not only surprising, but it also provides us with more information than a likely outcome. In the next part of this series, we will look at entropy as a measure of surprise.